Hello there and welcome back to this video series on control systems. Before we go into the video, let us quickly see what is covered. We have seen that a linear system satisfies the principle of homogeneity and superposition. And also we have seen that if a delayed input signal produces the output delayed by the same duration, the system is called time invariant. And LTI is an abbreviation of linear time invariant system. After watching this video, you will be able to define what is a transfer function and then specify what are analogous systems. You will be able to appreciate the content in this video and thoroughly understand it if you have thorough knowledge of Laplace transforms, of derivatives, integrals, then properties of Laplace transforms, and you know what you mean by initial conditions. Video 009 in this series gives a little bit about this discussion, and thorough understanding of this video would perhaps help a lot in going through the content of this video. Consider an LTI system described by this differential equation. This system obviously is an LTI system because it is described by a linear differential equation with constants. A1, A0, B1, B0 are constants, and thus this is a LTI system. Now take Laplace transform on both sides of this equation to get what is shown here. Laplace transform of this whole on the left hand side of equal to sign is equal to Laplace transform of this whole on the left hand side. Because Laplace transform satisfies linearity condition, you can easily see that you can take this Laplace transform into the braces. A1 times Laplace transform of dy by dt plus A0 times Laplace transform of y of t is equal to the same thing on the right hand side. B1 times Laplace transform of dx over dt and B0 times Laplace transform of yt. Now if we define capital X of s is Laplace transform of time domain function x of t, and capital Y of s as Laplace transform of time domain function y of t. Then using the property of Laplace transform of derivative that we have already seen perhaps in video 9, you can write Laplace transform of dy by dt is sys minus value of y at time t is equal to 0. Similarly, Laplace transform of the derivative dx over dt is equal to s multiplied by Laplace transform of x of s minus x at time t is equal to 0. Thus, in a sense, we may say derivation in time domain may be considered as multiplication with s in Laplace domain. Of course, you have a minus y of y at time t is equal to 0. Here also you have minus x at time t is equal to 0. We will use these values of Laplace transform of derivative here, Laplace transform of derivative here, and substitute them into equation 1. Okay. Let me quickly show you where is equation 1 in the previous slide. This is equation 1. If you substitute these values into equation 1, you get A1 times sys minus y0. This was Laplace transform of derivative of y of t. A0 times y of s. The same here, b1 times Laplace transform of dx over dt, and this is b0 times Laplace transform of x of t. This y0 and x0 are called initial conditions. That is, at time t is equal to 0, y of t is 0. At time t is equal to 0, x of t is equal to 0. If these two quantities are 0, then we may simplify this whole expression as shown here. A1s plus AO, B1s plus BO, both operating on y of s here, x of s here. Then you can take this x of s onto the left hand side this A1s plus AO onto the right hand side to write this equation 2. The ratio of y of s over x of s given in this equation 2 is called the transfer function. Thus we define transfer function of a linear time invariant system as Laplace transform of the output to the Laplace transform of the input, ratio of output Laplace transform by input Laplace transform with all initial conditions as 0. That is, system is starting from rest and then you will take Laplace transforms and find their ratio. We note that TF is defined for LTI systems only. For nonlinear systems, it is not defined. We note that several characteristics of an LTI system may be inferred from its transfer function. So transfer function is an important step in analyzing a system. Okay. If the transfer function of one system is the same as the transfer function of another system, then these systems are called analogous systems. Thus, in the sketch below, if you have a mechanical system with input x of s and output y of s, similarly an electrical system with input u of s and output v of s, and if you take the ratio of ys by xs, call it transfer function T1. Similarly, you take the ratio of vs over us and call it the transfer function T2, of course with initial conditions 0. Thus, if T1 is equal to T2, then this mechanical system and this electrical system are said to be analogous. We'll try to see about this electromechanical analogy in a subsequent video. That's all we are going to see in this video. To summarize, we can say that TF is defined as Laplace transform of output to that of the input with all initial conditions 0, that is with system at rest. Several characteristics of LTI systems may be inferred from its TF. So writing the equations and deriving TF is an important part in design and analysis of control systems. This process of writing differential equation and finding the TF may be broadly called modeling, though there may be more rigorous ways of expressing it. Similarly, the process of inferring useful information from the TF and then performing a design sequence may be termed as analysis. Some people say design is out of the scope of analysis. That's all we have for now. Have a great day.